Okay, great. We're going to do this. The theme of today is error. It is so important. This is huge in any kind of work, whether it is experimental or theoretical. You are never going to have exact certainty about anything, and you always need to quantify how uncertain you are if you're going to make strong claims. So let's do it. This first video will be a little bit shorter and is mostly background information. It's not stuff we'll directly use, but I want you to be aware of it. And then the second video will really be the actionable stuff, which takes us to the main point, and here it is. Error is how far away you are from the true value. So if you imagine, oh, if I had perfect knowledge and if I had infinitely accurate calculations and all this business, what would the truth be? Okay, that's an ideal, and you never actually get it. You're always some distance away from that true value. Now, I say distance, but I do want to be careful about emphasizing that error is signed, that you can have a positive error, you can have a negative error. That is to say, you can be above or below the true value of a quantity. So, when we talk about error in doing computation, then as much as we could get into all the details about all the things, we're not going to do that. Or are we? Because I'm like, well, it would be silly to put everything in one slide, right? Obviously, I'm going to do it. Here we are. Bam, bam, bam. Actually, this is kind of it, though. Like with any field of study, if you look at it super shallow, you're like, that's all there is to it. But then when you get into the details, of course, it can become very complicated. But in this video, we'll look at rounding error and truncation error. We are not looking at method specific errors in this course, but if you end up doing computational work, then knowing about the accuracy limits of certain algorithms, there are formulas that have been solved for that will say, what is the error in this kind of calculation or the error in that kind of calculation, where these things have been worked out for you, and those formulas might be relevant. But in this course, we're sticking with introductory stuff. Normally, I wrap with why it matters, but I actually want to front load why it matters because this can seem very abstract and very like, why do I care? So I want to give some grounding here. As I said at the beginning, all of your errors are always present. Like every answer you give is wrong. But just because it's wrong doesn't mean it isn't useful and doesn't mean it isn't good enough. That's the question you have to ask, is not whether there is error present, because the answer to that is just always yes. The question to ask is my answer close enough to the truth that it lets me do useful work? That's what you have to deal with here. And so knowing about these different kinds of errors ultimately helps you quantify the uncertainty in your results, which then lets you do useful work with your results. Because if you don't know how far off they are, then they're kind of useless. It's like, I got 7 for the answer. Okay, 7 plus or minus how much? I don't know. So is the answer 1 or is it 35? I don't know. That's why you have to know this stuff. But there are two particular real world examples that I want to give. Um, One of them is about the importance of small numbers, and then the other is really about straight up computational numerical error. So, talking about small numbers for a second, I want to talk about the GPS system. This is something that most of us use every day because if you use anything with location services, there's a GPS component. Um, so, when you're doing work with GPS, when you're using it, you're talking to satellites that are in Earth's orbit. And I have to use my physics for a moment here. Satellites in Earth's orbit are dealing with a couple effects that slow down and speed up the clocks of the computers on those satellites. So when we look at special relativity, these satellites are going very fast, and so there's some speed dependent time dilation happening that slows down their clocks. But there's also general relativity, there's the effects of gravity. And so these satellites that are orbiting the Earth are in a weaker gravitational field than clocks on the ground because they're further away from the Earth. And that has the effect of speeding up the passage of time on those satellites. So when you do all the math and you put these effects together, you find out that the clocks on satellites run about 38 microseconds faster per day than clocks on the ground. And you're like, cool, 38 microseconds. That's a small number. Yes, it is. If I'm off by 38 microseconds in literally anything in my life, I generally don't care. However, this is where I want to make the point about the importance of small numbers. A day later, these two clocks disagree by 38 microseconds. But then you're going to multiply that tiny error in time by a very large number. You're going to multiply by the speed of light, 3 times 10 to the 8 meters per second, so that you can find distances. To convert time to distance, you need the speed of light. And so when you take this 3, 3 or 4 times 10 to the minus 5 seconds, multiply it by 3 times 10 to the 8 meters per second, look at those orders of magnitude, we end up with something like 10 to the 3, 10 to the 4 meters of difference, 10 kilometers. That's like the it's about 6 miles is one way of thinking it, but, like, that's really far. That's my drive to work. So imagine your position being wrong by that much after a single day when the root cause of it was a difference of microseconds, a very small number. This is relevant in material science. Like, I know this isn't actually a physics class, but in material science, we often have numbers with very wide order of magnitude ranges. If you look at electrical conductivity, for example, materials, the most conductive materials and the least conductive of materials, they're like billions of times apart in their conductivity. It's crazy. So we actually do deal with very large numbers. I mean, Avogadro's numbers 10 to the a lot, right? 10 to the I don't even remember now. 32, 26, 23. There's so many exponents. Who can keep them all straight? There's a lot of atoms in a single teaspoon of stuff. So huge numbers are part of our game, and multiplying a big number by a small error can give a big error. That was the point of all that. And it is relevant in materials because we deal with big numbers. Okay. A second example I promised was actually computational error. So this is about the Ariane rocket, the Ariane 5, which was launched by the European Space Agency in 1996. And what happened in this rocket is it blew up like a minute after takeoff. So that's really unfortunate. It was unmanned, fortunately. No people were injured, but $500 million dollars literally exploded in the air. So that's a bad time. And of course, people want to know, why did this happen? What was the root cause of the failure? And the root cause of the failure was a software failure. It was a calculation problem where when they converted a 64-bit number, a 64-bit float specifically, to a 16-bit signed number. So, they're going from a decimal positive value to a positive or negative value. Um, that error was outside, or sorry, the value was outside of the allowed range of the variable. And so the variable came up empty. The rocket didn't know what to do. Its guidance failed and it blew up. So, yeah, the consequences for this stuff can actually be extremely real. Who doesn't love a good engineering disaster where money is wasted but nobody got hurt? It's the best kind for teaching purposes. Okay, so I've brought up variable types. I've talked about rounding error. And while rational numbers have finite decimal expressions, we have a lot of numbers that are important in math that are not rational and have to be represented in decimal form by an infinite decimal sequence. Now, our computers don't have infinite memory. You can't store all the digits of pi on a computer, but you use pi in calculations. And even if you have, I think I wrote 16 digits here, um, but we are, at the end of the day, we're rounding the values of these numbers. We're getting them to decimals that are really close to the true value, but not exactly equal to the true value. And as you do more and more and more and more calculations, those errors accumulate. Yeah, if you do one single multiplication, then maybe it's not a big deal. But think about when we're doing engineering simulations, like if we're doing a finite element analysis of some system and looking at stresses and strains in the structure of it, we're not doing a single calculation. We're solving differential equations over and over and over and over, and we are doing literally billions or maybe trillions of calculations. And if every one of those calculations is a little bit wrong, you really got to start to keep track of that so that you can make corrections. So that's rounding error. And it really comes down to the fact that our variables are finite in size. Now, we have different variable types. Some of them are more precise than others. If you want to know details, get into the documentation. There it is. For our purposes in this class, floating point numbers or floats are going to be sufficient for most, if not all, of what we do. But there are like double precision and extended precision variables that have even more decimal places if you need even more precision for a certain task. So there you go. That's a thing. Of course, there are more details to that, but I'm going to leave it to the CS majors for that one. I want you to be aware that this exists and know that you may have to choose higher precision variable types when working with tasks where error considerations are very demanding. The other type of error you've already encountered because you've already done it in your homework. I just didn't call it by its formal name yet. And so here we are. Here it is by its formal name. It is truncation error. So, this thing that you've been doing in your work is that you have taken functions and approximated them with series expansions. We've been doing Taylor expansions. There are other series expansions for functions. There's nothing magical about choosing polynomials as your basis. You could express things in terms of frequency components and do a Fourier series. There's many choices out there, but we are taking these theoretically infinite continuous smooth functions, and we're approximating them by a finite sum of terms. And we're not doing an infinite series because we don't have infinite time and space and calculating power. We chop off the series at some point and we're like, ignore all the rest of the terms. They're small. Well, okay, they're small, but they're not zero. And I wanted to show an example here. So this is the arctangent function. And in red, I have the official arctan function, at least according to Desmos. And we have now some different series approximations for arctangent. These are the Taylor series with increasing number of terms present. So in blue, we have the linear approximation. That's just arctan x approximately equals x. And at small angles, less than zero point 0.2 or so, you can see it's actually really close, but then they start to diverge. So you say, all right, well, if I want to go to larger values of x, then I'm going to need additional terms in the series to correct for the fact that arctangent is curving away from the line y equals x. So you subtract this 1/3 x cubed term to bring the approximation closer to arctan, but it actually overshoots. And so we get this green line that is below the arctangent function. Then you say, okay, well, now it's too low, so I have to add another term to get back up to where I need to be, and you get the purple function, but then that overshoots, so you subtract another term, and while this might sound a little wacky, too big, too small, too big, too small, if you look at the magnitude of the error, it is actually decreasing as we increase the number of terms in the series. So comparing the red function to first the linear approximation, I'm going to do this at x equals 0 0.8. So here is the distance between arctangent and the linear approximation. Pretty big distance compared to there is the distance between arctangent and the two-term approximation. You can see the two-term approximation is much more accurate. Then, if I want to show you where the three-term approximation is, I'll just clean this up, then the three-term approximation is even closer. The distance away is only that far. And the four-term approximation is really close. The distance is only that far. So you see, as we add more terms in the series, the truncation error is reduced because we are throwing away fewer terms in the approximation. And there is a notation for this and a name for this. So it's called Big O notation. O stands for order of magnitude. And it tells us about the order of magnitude of the accuracy for this approximation. to compare to another example, the exponential function. So here's our familiar Taylor series for e to the x, 1 plus x squared over 2 plus blah, blah, blah. But we're dropping the blah, blah, blah. We're stopping after the quadratic term. So that means that the cubic term is being thrown away. And that is the order of the truncation error. It's order of x cubed, saying that the amount of truncation error is proportional to the cube of the value of x. And so that's what the large script O here is representing. Now, if our series is converging, which it better, then in most cases, the value of the error, so not just the order of magnitude, but the actual number for it, will have an upper bound of x cubed. Because you know in the series, the next term is x cubed over 3 factorial. It's 1/6 x cubed. And so the error is going to be, smaller than x cubed in general. So those are our computational errors, but computers are hardware. Code is run on physical systems, which are made out of materials, last I heard. And so there is actually a true materials problem in this as well. In addition to these rounding errors and these truncation errors, sometimes a physical error will occur where the value of a bit in memory gets flipped. And so this will change the values of numbers that are stored in memory, which of course then goes into the calculations. And this phenomenon is called a bit flip. It's a very clever name. They're actually quite interesting to look into from a hardware point of view because there's really interesting materials questions here. How do you engineer a memory material that is going to be resilient against thermal noise and especially in harsh environments, things like outer space or like military hardware? You need materials that will be resilient against radiation damage. Radiation can cause bit flits to happen if a bit of ionizing, a particle of ionizing radiation strikes your memory chip, then that can cause bit flips to happen. So, actually, pretty interesting from an MSE point of view. All right, a little bit of vocabulary, and then we're going to wrap this up. So, here's our vocab dump for the day. The error, as I have said before, is the distance conceptually, but the calculation is observed value minus the true value. Now, this is a signed number. It is positive if the observed value is too large. It is negative if the observed value is too small relative to what the true value is. You can take the absolute value of that number if you just want to know the magnitude of the distance. And so then that's absolute value of delta x. That's the absolute error. The relative error is then taking this fractionally. Compared to the true value, proportionately is the error large or small? If delta x is small compared to the true value of x, then that is a small relative error. This will give you a small fraction. Finally, it's a fraction, so you can convert it to a percentage. And the percent error is then 100% times the relative error. And since this is acting not on the absolute error, but on the error itself, delta x, the percent error is also signed. If it's a positive percentage, our value is too large. If it's a negative percentage, the value is too small. And that's everything. So we're going to wrap this up, and I'll see you in part 2.